Thank you so much, and a great pleasure to be here. I just going to clarify one point. Lovely, lovely introduction, but one slight clarification. I'm not going to show my work. I'm going to show Nikki and Yu Yang's work and explain it as someone with a background in pediatrics. So we're going to talk about the clinical picture here. I receive research funding from a number of sources, including biomarine pharmaceuticals, and always disclose this before talks. So, what is ReNU syndrome? It is described as a form of developmental delay, a global developmental delay. And this is a description given for this constellation of symptoms. To some extent, once you see one of these symptoms, you can almost write the list that goes down it. This image here, taken from Nikki and Yu Yang's paper, shows in grey what you see in neurodevelopmental delay across many, many genes. And then in teal, we see the colour for a variant in ReNU syndrome. What you will notice is generally it's higher in ReNU syndrome than NND, suggesting it's one of the more severe phenotypes. We call it delayed walking and delayed speech or developmental delay. Here's an example of a normal development. This might be speech, it might be cognition, it might be walking, and we expect a child over time to develop in that normal range. In developmental delay, that normal development is delayed, unsurprisingly. But over time, that delay means that you are moving further and further and further away from that top typical range. And at some point, we stop calling it a delay and start calling it an impairment with the expectation it's not going to change. And so this developmental delay really means that these people are severely affected, making just basic day-to-day actions very, very challenging. We see delayed walking, delayed speech. That often goes with seizures. Seizures can be a very, very severe phenotype. They can even, in many disorders, lead to fatalities. I don't think we've particularly seen that in this syndrome yet, but it may be something which comes along because seizures can be deadly. We also see growth delay. This is somewhat common, but maybe more pronounced in ReNU syndrome than others. But all of these tend to go together as being a common group you see as global developmental delay. Perhaps one which is maybe slightly more unique is brittle bones. This is not a common diagnosis you see in developmental delay, but seems to be somewhat pronounced in this particular syndrome. And that could have big implications as we think about looking after these children and then as they become adults. I'd then like to draw attention to this characteristic here, so microcephaly, which is a sort of medical code for small head size. So here you can see that the ReNU syndrome bar is really, really distinct from other neurodevelopmental delays. And so that suggests this is really a kind of core bit of the phenotype. And I highlight this because I think it gives us some of our first insights into what might be possible therapeutically. So pediatricians really like to measure heads. It's one of the kind of core skills in training. The good news is if 3 pediatricians measure the same child, you will get 3 completely different numbers. But we plot them on these charts here. And the basic idea is you have some form of age on the bottom axis, the size of the head on the y-axis, and then a typical range. And we sort of plot length and height and weight all together. And you can see here on the far left, these are individuals with ReNU syndrome. Each red dot is an individual. All of this data is female because it's split female-male, and they're largely the same. What you can see here is most of those dots are within the normal range. Maybe a few of them tending lower, some of them quite well below the line, but most of them are in the normal range, suggesting that at birth, that's the line at 40, most individuals have a fairly normal head size. In the middle, we see up to about 2 years. Here you can see there's not many cases, but starting to trend a bit more below the line. But by the time we get to 5 years and onwards, most of the dots are a very, very long way below the line. So this would be called an acquired microcephaly, suggesting that what it begins off with being mild, not very bad, ends up being quite severe. And this suggests either that there's not been healthy division of the cells there, or that there is loss of neurons and cells along the way. So this starts to raise a question about when could you treat it and how much impact would you have as you went through the treatment pieces? Of course, we don't know the answer to that, but it starts to give a first insight. Critically, it looks like there's likely to be some window opportunity. What we don't know is how much you could rescue at the far end. So if we wanted to treat it, how would we do it? We need to understand a bit more about exactly how ReNU42 leads to symptoms. And to get this, we need to start off on the left. This represents all of your mRNA, everything, all the instructions being made by your nucleus, creating that mRNA, which is then going to go on to make the proteins, all of your proteins that build you. Now, between these two is a process called splicing. For some reason, genetics has a bit of a reputation for being a little bit scary. Within genetics, splicing has a reputation for being even scarier. So I want to try and find a way of making it presentable in a happy, nice way. So here's a spliceosome. So this is the bit that does the splicing. This is a happy spliceosome. And it works out basically, where am I going to modify this RNA, cut it together, dice it up to make the right protein. Now, of course, the spliceosome is happy, but it needs to know where to cut. And for that, it needs a friend. And here is where ReNU42 comes along. And ReNU42 basically says, this is where you should cut. Here, come along, spliceosome, let's be happy, let's make proteins. Now, again, I said none of my own work, again, presenting work from Nikki and Yu Yang. It seems likely that if you only have one copy of ReNU42, things are probably okay. There seems to be enough of it around. Probably the spliceosomes are still happy and doing the right job. It seems very, very likely, based on the fact we've never seen someone with it, that if you have no copies of ReNU42, the spliceosome is not happy. And if I just flick back, if you watch the proteins, there's your happy normal protein with different amino acids. It's now become an unhappy protein. It's wrong. At best, it's got a couple of wrong amino acids. At worst, it's not making any protein at all. And so then this is ReNU syndrome, where you've got one copy of ReNU42, which has got a single variant in it, which causes it to do something different. And as I looked at this picture, I was thinking it was like the kid who tells you to go behind the bike's veg and start smoking. It leads the spliceosome astray. And that means that some of the proteins being made are now not being made correctly. Remember, this is all of the proteins. And so we would call this a gain of function or a toxic allele approach. I think with a few I's to dot and being sure this is it, but it seems incredibly likely this is how it's going to go forward. And if that's the case, a therapy would look like this. It would be reducing the sort of naughty copy of ReNU42 whilst leaving the other copy alone. Because we know if there's no ReNU42, that also leads to an unhappy spliceosome. So that's what therapy needs to achieve, decrease that one. Now, the good news is there are molecules capable of doing this, and the discovery of this disorder has been at a time when these molecules have become in clinical practice. We know DNA makes RNA. If we take the opposite strand to RNA, that would be called antisense. So this is an antisense oligonucleotide. And it binds to the RNA, therefore interfering with how that RNA acts. And you can do various things with it. You can interfere with splicing. You can also decrease the amount of RNA. It is chemically modified. This makes it very resistant to being degraded and also to bind tightly to the RNA having an effect. So if we go back to ReNU42, and I just want to add a disclaimer here, this is not the real sequence. That's not because I don't know how to find the sequence. I want to be really clear on that. It's just that I don't want to publicize something which might one day be a therapy, because you might claim I'd revealed the secret sauce. It'd be hard to secure it to get it to the patients. So here's some sequence which might be ReNU42 but isn't, but let's imagine it is. We then have the insertion of this extra base pair. That's what's causing the problem. We would then make the ASO, which is the opposite version. It binds to that version, and it needs to recognize the difference between the U and the A. It's a bit to ask of an ASO, but there is precedent of being done it. Unfortunately, we have some of the sort of leading experts in the world helping us to think about what this might look like. And so the hope is that this could work as being a therapy, reducing that bad copy. And if we could do that, the hope is that maybe you could move the person from that delayed developmental trajectory to the upwards one. And that was what this looked like in the clinic, is every 3 months or so, the child having an injection into the back, a bit like an epidural, and that injecting the product to get back there. I'm going to end by saying thank you to the group here. I just want to be a bit un-British and just voice the amazingness of what we see here. This couldn't have happened in any other country or any other place in the world. It needed Genomics England and the insight to create this data in the first place, and then the amazing people who work at Genomics England to do it. It needed the patients to be brave and give their data for research. Without them, none of this would be possible. It needed two spectacular scientists as a team together to find this. What they maybe didn't show in their talks, it is incredibly hard to find genetic mutations. I mean, really, really, really difficult. And then also this data is completely public, well, not completely public. It's accessible to all researchers willing to go through a research procedure. Anyone could have found this, but no one else did. It was this team who found it. And then lastly, we have the amazing work of the UK Environment and Unique and Sarah of being able to then support this to make it into something more than just a diagnosis, but actually already a functioning family group with guidelines and ideas and support for the families involved. And so with this, what I have witnessed as an observer seeing this is what took 20 years in other single gene disorders happening in 9 months. And so with that, I think we have an amazing team who hopefully will drive this forward. And I look forward to it, presenting other people's work as an exciting update in the future. Thank you very much.